pruning ratio is too high, we will get the similar result as shown in the lottery TT paper. But if the ratio is not too high, we can still tune the learning weight, and it is still possible to train with totally randomized parameters. So above all, I would like to choose the structural pruning, like pruning the filters instead of the weight if possible, because it is more easier to train the subnetwork. And also because pruning the individual weight will result very irregular architecture. So it would be hard to implement and speed up in the training and the inference stage. At the end of this part, I would also want to quickly mention two more things. The first one is that it would be helpful to train the network with regularization terms. For example, we can use L1 or L2 regularization to encourage the sparsity of the network, so we will be easy to prune later for sort the importance. And the last thing is that we actually need to pre-train the model before pruning? The answer is also no. So there's a paper trying to prune from scratch called "Could we prune from scratch?" Yeah, but I will not show here. So now let's turn to the first case study, which is called the deep compression, before going to the other methods. So deep compression includes the pruning and quantization methods as we presented in the previous slides. So the above figure shows the overall pipeline of their method. They firstly prune the network by learning only the importance connections, which is a very normal individual weight pruning. And next, they quantize weights to enforce the weight sharing, as Yingjie mentioned. And finally, they apply the Hoffman encoding to encode the weight bits and the index bits. So let's look into different parting details. So the pruning is just a very basic network pruning, weight pruning. They prune the small weight connections that below a threshold are removed from the network. And then they retrain the network to learn the final weights for the remaining sparse connections. And after the individual weight pruning, they store the index weights as key value pairs because connections are very sparse. And further, they try to store the index differences instead of the absolute positions. For example, you have 256 parameters, so you need 8 bits to store the absolute positions. But if the largest difference between two indices are only 8, then you only need 3 bits to store the differences between the indices. And then you can recover the indices and the weights pairs without loss. And for the quantization part, they use the k-means clustering to identify the share weight for each layers of the trained network. So that all the weights that falls into the same clusters will share the same weights. And so here's the same picture as Yingjie shows previously. And they also examine 3 different initialization methods for the clustering centroids. Then they try to use a Hoffman encoding. The Hoffman encoding code is an optimal prefix code commonly used for lossless data compression. It uses a variable length code word to encode the source symbols. So the encoding tables is derived from the occurrence probability of each symbols. So more common symbols are represented with few bits. So the figure above shows the probability distribution of the quantized weights and also the sparse matrix index of the last fully connected layers in the AlexNet. So as we can see here, both the distribution are biased. So most of the quantized weights are distributed around the 2 peaks, and the sparse matrix index difference are rarely below 20. So experiment shows the Hoffman encoding this non-uniform distribution values will save around 20% of the network storage. So here's the result of the compression rate and the corresponding classification performance for the original model and also the compressed model. There are 4 basic networks here, 2 on the MNIST and 2 on the ImageNet dataset. The network parameters are and the accuracy before and after pruning are shown in this table. So the compression pipeline saves the network storage by 35 to around 50% across different network without loss of accuracy. So we see the deep compression is very promising at that time. And here's the compression statistics of different layers for the AlexNet and also the VGG16. So as we can see here, the AlexNet can be compressed to around 3% of its original size without impacting the accuracy, while the VGG16 can be compressed to around 2% without loss of accuracy. So this paper also shows the accuracy at different compression rate for pruning and quantization together or individually. So let's just ignore the green line here. So when working individually as shown in the purple and the yellow line here, the accuracy of the pruned network begins to drop significantly when compressed to below 80% of its original size. And when the accuracy of the quantized network also begins to drop significantly when compressed below 8%. So as shown in the yellow line. But when we do combination, as shown in the red line, the network can be compressed to around 3% of its original size without loss of accuracy. So this implies that combination is a better choice than doing individually. And they also try to do experiment on the centroid initialization. So this is more practical aspect. So it shows that the linear initialization is a best choice for the k-means initializations. So about 4, in conclusion, the deep compression paper is a very old paper, but provide a very typical method for the network compression. So now let's turn back to the methodology of the network compression. So let's turn to the low rank factorization. Li Hao.
Hello.
Hello.
Can you hear? Hi.
Yes.
Okay, so for the quantization and the pruning, we try to remove the insignificant parts of the network. If we take a little step back and look at the form of the weights and parameters in the network, they are represented as matrices or tensors. Here, this figure shows the filter matrix of a convolutional network. You can see that the filters themselves have certain structures or patterns. This indicates that they are actually store low dimensional information. So such a form as matrix or tensors has redundancy in itself for the training. So it provides another opportunity to compress the model through decomposition. By decomposition, it simply means that we rewrite the original matrix or tensors into more simple components. So in this slide, I'm going to show you the idea. So on the left top corner, we have 2 vectors, a horizontal one with n dimension and a vertical one with m dimension. If we multiply these 2 vectors, we can get a rank 1 matrix, which is m times n size. Now, if we have several of these rank 1 matrices and sum them up with weights, we can construct many new matrices. Now, the question is, can we do the thing to the other direction? Not the construction, but the decomposition. And it turns out that we can actually do it. And we can actually do with a small number of this rank 1 matrix. Now, if we grab a random matrix, and we rewrite it in the summation of several rank 1 matrix, and the minimum number required for the rank 1 matrix is R, then we call them the random matrix has a generic rank R. It's a rank R matrix. And this idea can easily apply to higher dimensional tensor. A matrix is simply a 2D tensor, and we can do the same thing with a 3D tensor by simply adding another vector to the product in construction of the rank 1 3D tensor as shown in the right bottom corner. And then we decompose it any 3D tensor with rank R using R numbers of these rank 1 simple tensors. And we can write it in a mathematical notation as shown in this slide for a tensor field F expanded by D vector spaces F1 to Fd. Any tensor in the tensor space A can be represented, rewritten in the form as a weighted summation of R numbers of rank 1 tensor. So we apply this idea to the convolution network. On the left top corner, you can see it's a full convolution represented as a 4D tensor with size S times D times D times T. The input dimension is S and the output dimension is T. D times D is a future dimension. And on the bottom, you can see we use R numbers of rank 1 4D tensor to represent the full convolution. And each one of these rank 1 tensor is simply the product of several vectors. And in this way, we decompose the full convolution tensor. However, in practice, we don't do the exact decomposition. We use an approximation as long as the reconstruction error is below a certain threshold. And using this approximated decomposition, we have to fine-tune the network after the decomposition, and we do it layer by layer. We first decompose the first layer and keep it fixed, and then fine-tune the rest layers, and we move on to the next layer. And iteratively, we decompose the whole network. However, this process is really time-consuming. So in order to tackle it, is another straightforward idea. So in the end, we want to rewrite the matrix or tensors in the compressed form, the decomposition form. So why don't we design the structure of the network initially in this form so that it's forced to be trained into that form. So this is called structural regularization. And this idea will be explored later in the presentation by Yiping called compact network design. Now, I want to rethink about the deployment problem. The problem is that we have a goal we want to reach. And in the environment A, with some constraints in this environment, we collect some data and train the network, and we get a working version state system to deal with the goal. And the deployment is simply we want to deal with the same goal in another environment, for example, environment B. And as we already have a working version in environment A, so you can simply transfer the network with its parameter to the new environment as long as they satisfy the constraints in the new environment. However, it is not necessarily the case because in the environment B, it could be a totally different system. We cannot directly use the network, the parameters. So in that case, the straightforward idea is to transfer the data and design and use a completely different system to train a completely different working version in the environment B. However, there's another approach between these two sides called the knowledge transfer. So the knowledge transfer simply means that when we want to transfer, whether we use a network or data are not important. What we want is that the knowledge about the goal or task to be transferred to the new environment B. So if we have a way to explicitly represent the knowledge, then we can directly transfer the original knowledge in the environment A. So as for facts, in fact, in the case of ensemble model, an explicit representation of knowledge is easy. We simply fuse the outputs of the models in the ensemble and train a small model to learn the fused outputs of the ensemble. And this work has been done in 2006 by Corona. And it turned out that learning from the fused outputs of the ensemble outperforms learning directly from the original data. And this learning from the outputs can be generalized to classification, which is done by Hinton's group in 2015. They brought up the idea of knowledge distillation. They use a teacher-student scheme where the teacher model is the trained model, and the student model is to learn from the trained model. So for a classification problem, the output of the trained model is simply the probability of which data belongs to which label. The trick here is that instead of learning the exact probability, we add a factor to the logits in the softmax. So if the t is larger than 1, we flatten the probability. So it's a rough classification. And if we want the student to learn that rough classification, we can build a loss function called distillation loss. And at the meantime, we can still let the student learn from the hard label, the ground truth. And that is a strict classification. We call it student loss. And the total loss is the weighted summation of these two loss. And it turns out that this idea actually works. As you can see, the distilled model performs significantly better than the small model directly trained from the original data. And for other problems, there are other representations. And here are some three papers working on other representations. And we're not going to go into details about them. Instead, now I want to come to the really interesting part, because if we apply the distillation idea to decentralized learning, if you remember the teacher-student scheme, there's a discrimination between them. However, if we throw the discrimination of teacher and student and have two same networks, and now we have a symmetric situation. So the distillation can go both ways, and it can go along the training. So that is the idea of co-distillation. We start with several same networks, and we run some BERT steps to make sure that they have different aspects of the data. And then we train them together. Notice the difference between the co-distillation in decentralized learning and the stochastic gradient descent is that what we communicate is not the gradients of the parameters, but the exact parameters of other networks. So we learn from the output by getting the exact parameters of other networks. And if we use a stale update of other networks parameters, we get a very efficient communication scheme. And this co-distillation can be applied to very large network training. And in this figure, I show you the convergence rate of the training. You need to focus on three lines: the pink line, the green line, and the red line. So the pink line is simply synchronized decentralized stochastic gradient trained on 128 GPUs. And the green one doubles the computation resource using co-distillation. And the red one uses an ensemble model and then distill the model to a new network, as we seen in the 2006 paper. So by comparing the green one with the pink one, we can see that the code distillation, while doubling the computation resource of code distillation, we have around 2 times faster convergence. That means the code distillation keeps the trade-off between the resource and convergence rate, while the synchronized stochastic gradient descent does not do the same. It has an optimal point, optimal amount of computation resource due to the distribution of the data. If the data are too distributed, the convergence rate cannot decrease anymore. So the code distillation breaks the limits of the size of training network. And that sums up our presentation of the knowledge distillation. And for the next part, we give it to Yiping about the compact network structure design.
Okay, so one way to compress and accelerate the model is to optimize the execution and storage, like we introduced before, pruning, quantization, low ramp factorization. And another parallel way to do that is directly design a more efficient but low-cost network itself. And to do that, there are lots of small tricks. The first one is to use one-by-one convolutional layer. Because one by one conv filter has 9 times fewer parameters than 3x3 computers. And but to be noticed that if the feature map only have channel 1, then a one by one conv layer doesn't do much. But if we have more than 1 channels like this in the feature map, then the one by one conv is a pretty good idea. And another thing is to use global average pooling instead of fully connected layer. In the model compression, lots of networks are designed to run classification, and in classification, the fully connected layers took lots of parameters. And to use global average pooling instead of that, we can save a lot of computation and storage. So the third trick is to use group convolution. Here is an example of normal two-dimensional convolution. So basically, we have a feature map with height h and width w with channels number dn. And if we want a feature map to have the output feature map to have channels d out, we will use a filter with parameters so this much. However, if we want to do a two-group convolution, basically we separate the feature map into 2 groups and then operate conv layers. Operate convolutional operations on these two splits and then concat them together. After that, we will get exactly the same dimension of the feature map, but we actually save the parameters by half. So imagine if we use a 4-group convolution, we can save the parameters by 1/4. Another trick is called depth-wise several convolution. Again, here is a normal two-dimensional convolution. We can notice that the feature maps has only 3 channels, but if we want to have 128 channels as the output, we need 128 of the filters. And that takes lots of parameters, of course, computation. But if we do this depth-wise several convolution, so the idea is that we first apply this depth-wise conv to this feature map, and then we apply this one-by-one operation or point-wise convolution with 128 of them, and then we get the exactly same dimension of the feature map with 128 channels as the output. However, we actually save a lot of parameters because we have 128 of one-by-one conv, and this doesn't take much parameters. So by doing this instead of a normal convolution, we actually save a lot of parameters. Here is the MobileNet version 2. Actually, 3x3 conv and batch norm and ReLU to depth-wise separable convolution. So they apply 3x3 depth-wise conv first, and then batch norm, and then ReLU, and then this one-by-one conv, and then ReLU, and then batch normalization and ReLU. But the problem with this is that the manifold collapse because of ReLU. So if you remember here, we have a ReLU here, but that could cause the problem. They show a toy example to illustrate this kind of problem. So assume we have two-dimensional features on the very left. So the input is two-dimensional features, and then we apply a random matrix T to map this into an n-dimensional space. And after that, we apply ReLU, and after that, we apply the inverse of the matrix T to project back to the two-dimensional space. And here it shows that with different n, we can actually recover, for example, when n is really small, like 2 or 3, we cannot recover the information. And if n is pretty big, like 15 or 30, we can recover that. So this gives us idea that if the numbers of the channels in the feature map is pretty small, say 2 or 3, and then we apply ReLU, we actually lose some information which would never be able to recover. So that's the problem that in MobileNet version 1, because we didn't care if the feature map has lots of channels or a small amount of channels. So we apply ReLU there, and then we lose some information. So they propose a solution that if, say, the feature map has a small number of channels, they can first apply this one-by-one conv here to make the numbers of the channels pretty big. So the thickness implies that it has lots of channels, and here we don't have much channels. So they can first apply this one-by-one conv to enlarge the channels, and then apply depth-wise separable conv so that we won't lose much information. Another problem with MobileNet version 1 is that they didn't reuse any features. Because the MobileNet version 1, actually, the idea comes up in that paper, actually it's pretty early. And after that, we have the ResNet, DenseNet, which shows that the feature reuse is pretty important. And they added that into MobileNet version 2. So basically, they proposed inverted residual with linear bottleneck to address these two problems. So on the left is the depth-wise separable convolution in MobileNet version 1, and on the right is the inverted residual with linear bottleneck. We can notice that So before we apply depth with conv, we actually use a one-by-one count to enlarge the numbers of feature maps. And here, in the very end, they use this linear activation instead of right loop, because they argue that here the numbers of feature map is not a lot, and they wouldn't want lose lots of information by using right loop. And they actually show that in the paper that the importance of using a linear activation here. And of course, they use this residual shortcut to reuse the features. Another thing they do is based on single shot detector SSD, they propose a mobile friendly variant of that SSD Lite. So the idea is that the idea in the SSD is that first extract feature maps and then apply conv filters to detect objects. And what they did is just they replace all the regular convolutions in the SSD with the depth-wise separable convolutions. And by doing that, they can save lots of parameters. And they use the total number of multiple as the computation cost. And we can see that we save lots of computations as well. And here they show that with the special design of MobileNet version 2 and the SSD Lite, actually they saved a lot of parameters during object detection task, and the computation cost is pretty low. And they did the experiment on a Google Pixel 1 phone, and on the phone that it would take 200 milliseconds to infer. That's pretty much all the tricks and in the compact network design. So if there are some questions, I think we are a little bit late.
Okay, so thank you very much for the presentation. Do you have questions from the attendees, the panelists? If you have, please raise your hand. Yeah, so Martin has a question. Yeah, now you can talk, Martin. Just unmute yourself.
Do you hear me?
Yeah.
Right, good. Thanks for a nice talk. I'm wondering a bit specifics on like the pruning methods, especially. How did you, when you read this paper, did you get any sense of how intricate it is to choose like the pruning hyperparameters? At what level do you like start? I understand it's like an iterative method, but did you get any sense how difficult it is to choose it?
Yeah, but in practical use, I think instead of choosing a specific threshold for example, for the weight magnitude, I think it will be better to choose the ratio of the remaining connections. So, for example, you choose to prune around like 20% of the parameters at one time, and you do it iteratively, right? So you can't. It's a bit hard to choose a specific threshold for the weight or the importance, but you can choose like the percentage of the remaining weight. So, and I do not see how they try to tune the hyperparameters in the deep compression paper, but I think it will cost time to tune the hyperparameters, as you said, and it quite tricky. And yeah.
Yeah, okay, yeah, thanks. I mean, when you have a very large network to begin with, I mean, this must take some effort to figure out the pruning.
Yeah.
But yeah, thanks.
And of course, as you mentioned, there are some hyperparameters like the lambda between the actual loss and the regularization term. And in many papers, they do not talk about this too much. But as far as I know, some of them try to use like L1 and L2 and do some comparison of different regularization terms, and they find that the regularization terms like L2 to encourage sparsity will help, but the L1 to push most of them to be zero of the weight, it will not, the final performance will not get some benefit from the L1 but L2. So it is more like a trick, but yeah, it is hard to say.
Yeah, okay, so we are running a bit out of time, and I suggest that we take the next question by Henrik in the virtual portal session, okay? So that try to keep the schedule now. So thank you very much for the special topic 3. And now, let me share my screen again. Okay, so now we have a special topic 4, and the topic is generalization error. The presenter is Martin Helfrich. So now let me promote you to panelist, and I hope you can you hear us? Can you talk now?
Yes, hello.
Okay,
hello.
Great, yeah. So now you can start sharing your screen, Martin, whenever you like.
Thanks. So yeah, do you see the presentation?
Yeah.
All right, great. So hi, everybody. I want to start with thanking the organizers for a nice workshop and also letting me present my own paper that I submitted together with my supervisor and a professor at our department. We submitted the paper. It's called Generalization Error for Linear Regression Under Distributed Learning. We submitted it to the conference Signal Processing Advances for Wireless Communication. And it was accepted, and it will be presented there next week. The paper presents an analysis of distributed learning of linear regression and provides intuition and guidelines for how to design these problems from the perspective of generalization error. So first I threw in this link. The paper is available on arXiv already, so you can find it there through this link. So first I will introduce the paper and give some motivation and background for the problem we consider. You might feel this introduction is a bit redundant given all the presentation that we have had already on distributed learning, but that was mostly yesterday, so I think it's good to get on the same page again. Then I will jump ahead a little bit to give you some notion on what the results in the paper, what the essence of the results are in the paper. And then I will take a step back and go through a little bit the basics, the linear regression, and present the performance measure that we consider in the paper, which is the generalization error. And then a bit on distributed learning in this specific problem. And then I will present the algorithm that we have used for our analysis. And then I will give some simplified simulation examples before we move on to the results, where I show you both empirical results and the main analytical results, of course. And then before I wrap up, I will show you some technical details on the proofs on how we found these analytical results. So you get some notion of that. Distributed learning, as we have talked about in this workshop, can provide a framework for sharing the high computational burden of the learning task over multiple nodes or workers. Distributed learning, specifically over wireless communication networks, is emerging and a significant facilitator, for example, in edge computing or learning tasks where privacy is very important, or also where communication resources are limited. Because we have all these communication efficient approaches to this distributed learning. In our paper, we consider the learning task where we have the aim of estimating an observation Y, giving an input A, and we have some parametric model f of x, where the parameters are x. This is, of course, in contrast to a non-parametric model for example, k-nearest neighbor classification, where you predict the label of a sample based on the labels of neighboring samples. But that's of course also a classification model, while we're today talking of regression problem. So the main aim of the learned model is to estimate y when a new input A comes. So we will be analyzing a distributed learning technique from the point of view of the generalization performance. And when I say generalization performance, we talk about how well the learned model is working, or how good accuracy it has on data that was not used for training to find this learned model. And we use the generalization error, which, I mean, a low generalization error is not typically guaranteed by having a low training error. So just because you're performing well on the training data, does not mean that you perform well on other data, on test data. And this is especially true when you have more parameters in the model than you have data to train it. Saying something like that, the model is over-parameterized. And this is often very common in neural networks, where you have maybe millions or billions of parameters and you have maybe hundreds of thousands of data. But these modern machine learning techniques that we have discussed, especially in the previous presentation, they often achieve a low training and generalization error, although it's very over-parameterized. Other studies that we have seen on different challenges for distributed learning are, for example, energy constraints, quantization, and privacy. And our contribution to the literature is this analysis of the generalization properties of a distributed learning scheme called COCOA, which was introduced in this paper in 2014. And there we consider the setting where the unknowns are distributed over the nodes rather than the observations. And this follows the line of work initiated in the 80s, actually, by the famous professor Dimitri Bertsekas. And our main analytical results describe the generalization error as a function of how the unknowns are partitioned over the nodes of the network. And using these results, we will provide some guidelines on how to partition or not to partition the unknowns in this distributed setting. And this slide here is just showing you a few things to keep in mind while we walk through this presentation. Some kind of tagline on what our paper is doing. And here you see the linear model, which you might think feels a bit simplistic to look at, but we think it is very important as a first step for this kind of analysis to gain some intuition and some notions on what to focus on if you move on to more complex model structures. And this paper is from the empirical. This figure is from the empirical results of the paper. And on the x-axis here, you see some partitioning parameters, which describes how the data is partitioned over the nodes. And on the y-axis, you see some error. And you see at some specific partitioning, the error is very high. Okay, so we are focusing this linear regression model, and we also focus on the least squares cost function. And in the matrix form, we describe it like this, where the A matrix contains the inputs. Each row is each input, and each entry in the y vector is each observation. And this x vector is then the parameters that we're going to estimate. And the way we find the solution to this in the ordinary centralized setting is that we take the pseudo inverse of this A matrix and we multiply it by the observation vector y. Something to note here is that this solution, this x hat, is not always the true parameters x. For example, in the over-parameterized setting where this A matrix is broad, then you often have infinite amount of solutions, and this x hat is specifically the minimum 2 norm solution. So the solution with the smallest 2 norm, or the squared 2 norm. So yeah, this is not always the only solution. Okay, so if we have some estimate x hat, so we have some y hat, a multiplied by x hat. So we've gotten this x hat from using this A matrix and this Y vector. Then we can measure the quality of x hat by this generalization error, which is defined like this. So we have here a new data point comes, the A star and the Y star. And given some distribution, defining this A star as a random variable, we define the generalization error as the expectation over this new input of this square prediction loss. So Y star minus the estimate of Y star squared. And more specifically, if we assume A star is a Gaussian random vector, we can simplify this expression and get this one. So the dependence on A star actually disappears, and the Y star, it pops out with this covariance matrix. So you only get this square root 2 norm of the distance. You get the distance between the true parameters and the estimated parameters. And if we also assume that the A matrix is a random variable, the A matrix that we use for training, and since we have used it to estimate x hat is then a function of this training data, and we will analyze the expectation over this training data of this generalization error that we already introduced. So this is the expression that we will think about when we talk about generalization error in the paper. So throughout the workshop, we have mentioned a lot of different ways that the data can be split or distributed over the workers or the nodes. I would just mention two straightforward ways of distributing the linear regression problem. And the first one is when the rows or the inputs and the observations are distributed over the nodes. So each node has one set yk of the observations and one set of rows from the A matrix. So they have all the full length of these rows. So node k will have nk times p input variables. And they will all, we can think of this setting as all the nodes contributing to the estimation of the complete x vector. So all the nodes will have something to say about the whole of x vector. Another setup, which is the one that we focus in this paper, then we instead give all the nodes access to the y vector, and we divide it by the columns over the nodes instead. So now they don't have the full length of the rows, but they have the full length of a subset of the columns. So node k will have access to this block, ak, and it will actually estimate a block of the xk corresponding to these columns in the AK matrix. So this is just a more in-depth view, and the structure, we just assume that it is ordered partitioning like this. So the A matrix is like this. This is the complete A matrix. And node 1 has access to the first set of columns. Node 2 have access to the next set of columns, and so on. And we assume we have, or we note the number of nodes as k, large k. So node 1 will then estimate the first block of the x vector, which will denote x1, and with this bold x here, and the second node will estimate x2, and so on. We denote the length of this block as pk. The number of columns in each block is pk. Correspondingly, in xk, you have pk variables to estimate, or parameters. So now I will give a brief introduction to the distributed learning method that we consider, which is COCOA, which stands for Communication Efficient Distributed Dual Block Coordinate Ascent. And we denote the estimate of the k part of x as x hat k, and we have this superscript to denote the iteration number. We initialize it at 0. We also have these auxiliary variables v, v bar and vk, which are also initialized at 0. And these two variables, or these variables, keep track of, we think of them as keeping track of the local and central estimates of the y vector. So this v bar will collect all the estimates of y, the observations from all the nodes, and average it. And this estimate that it's collecting is this vk. So each node will output one of these vk's, which is sort of a local estimate of the y vector. It's not exactly the local estimate because this vk is using this v bar to be created in the next step. So, but you get the idea. So the algorithm consists of two loops, one outer and one inner loop. And in the outer loop, we think of some central node or master node, which collects all these vk's and averages to get v bar. And then in the inner loop, that's the loop for the workers in the network. So the first thing to do is to update the parameter estimate x hat by computing this delta x. And as you see here, you take y minus v bar, and it is multiplied by the pseudo inverse of the block of the A matrix that this node has access to. So you can think of the first step where v bar is 0. Then this delta x will be just the local least squares solution to this y equals akx. You will add this to the previous parameter vector, and you will spit out the new one. And then you update this vk by taking the v bar from the central node and adding the local estimate that or an update to this estimate using the step you just took in the parameter vector. And then this vk is sent back to the master node, and it is computed, and so you iterate. Yeah, just to say that this is the unregularized version, so it's a bit simplified. If you would have regularization, you would have some extra term in here and also over here. So now I will look at some simulations of the algorithm where we have two nodes, and the problem is distributed like this. So the observations are created using random data in A and random data in A1 and A2, and with some fixed parameter vector x, which is partitioned into x1 and x2. So in the left example, you have 10 observations, and you have 6 unknowns distributed over the two nodes. So both nodes are here estimating 3 unknowns each. And on the x-axis, you see the iteration number, and on the y-axis, you see the generalization error. The centralized least square solution is just used, produced using A pseudo inverse times y. And it's, of course, constant because it's not an iterative algorithm. What you see is that the COCOA solution converges to the same generalization error as the centralized least square solution, and it actually converges to the same solution, which is the true parameter vector. So that's really good in this case, and they both get, of course, perfect generalization error in this case when they find the exact solution. In the right example, you see also 10 observations, but you have now many more parameters in the true parameter vector. So you have 30 parameters, and both nodes are estimating 15 each. So now neither the centralized least square solution or COCOA is converging to the true parameter vector, but the generalization error is not huge in any sense. It's just a bit off. So you have in the range of 0 to 1, but COCOA is a little bit higher than the centralized least square solution. And these two settings are both quite fine. And the algorithm is working pretty nicely in the distributed setting. So now we look at an example where it doesn't work as well, which is where P1 is actually equal to n, the number of observations, and P2 is some other number. You see the centralized least square solution is still giving generalization error low like in the previous example, while COCOA is giving a much, much higher generalization error. So yeah, this is what sparked our mind to motivate this paper when we noticed this kind of behavior. And we figured we wanted to explain this behavior. What is underlying here? Why is this happening? And that's what we are then explaining with our main analytical results, which I will show you in a little bit. But first we'll consider a more simplistic example where we just have one observations and two unknowns. So the data set is just this equation, y equals ax1 plus bx2. And we assume that these inputs a and b are non-zero, and so their pseudo inverses will be just 1 over a and 1 over b. And if we iterate the algorithm, we find this first step in x1 and x2, and that both v1 and v2 will be y. So what happens when you average these two, you get y again in the central node. And when you send this back to the workers, they will both get a 0 step because y minus v bar is 0. So the estimates will be x1 hat, x2 hat will be y over 2a and y over 2b. So now we want to see the generalization error of these estimates. So we take the expression that we had before, which was this x minus x hat norm squared. We simplify it a bit and we find this type of expression. And the important thing to note here is that you have a square, b square in the denominator, which were the inputs to the system to generate the y observation. And consider the setting where a or b goes or are close to 0, then this generalization error will be really, really high, right? So if you then think of the setting that we are analyzing in the paper where the data is Gaussian, you can't take the expectation over the training data over this expression because as a or b are close to 0, the integral in the expectation will diverge and you will have infinite values. And this is sort of giving you the main essence or notion of what happens in the analytical results later on. First, some more empirical results. Here we have two nodes again, with a bit larger setting with 50 observations and 150 unknowns in the system. And the sum of the unknowns in the two nodes are always summing up to the total number of unknowns, which is 150. But in this figure, we let P1, the number of unknowns in node 1, we let it slide from 0 to 150. And simultaneously, P2 will slide from 150 to 0 in the other direction. So here you see P1 on the x-axis and the generalization error on the y-axis. So what you notice that when P1 again is close to the number of observations, which is 50, the generalization error blows up. You get a really large increase in it. And also again at P1 equals 100, because that's where P2 is equal to 50. And in between, you have quite good generalization error compared to over here and over here. And you see close to 0 and close to 150, they were quite close to the centralized least square solution in terms of generalization error. You can just note that the results here are obtained after convergence of the algorithm. Okay, so now I will not tease you anymore, and I will move on to the main analytical results of the paper. So this is the big one, which we call theorem 1. And what we do here is we assume that the A matrix, again, we assume that it has Gaussian, zero mean Gaussian entries with unit variance. And the rows of the A matrix are IID, so the data is IID. We assume no regularization. And we here have an expression for the generalization error in the first iteration, after one iteration of the algorithm. Later on, I will give you similar expressions for larger iteration numbers, but we start here. And the expression we find here in equation 1 is, you see here, the sum over the parameters, the norm of the parameters in each node, the xk, we sum over all the nodes, and we multiply in each node by alpha k. And alpha k is defined in equation 2. So this is just the number of nodes, the large k, some factor here dependent on this one, and then we have this r min k divided by pk. And this r min k, you see it here at the bottom, is the minimum number of pk and n. So the number of unknowns in node k versus the number of observations. So this ratio will always be smaller than 1, right? Because the largest this can be is the largest number, or the either pk or n, and if you divide it by pk, you will have something smaller than 1. And then you see this last summation here, which is over gamma I. And here you sum over I from 1 to k, so over all the nodes except the node that we're looking at the moment, except the one corresponding to this k index over here. And this gamma k is defined here in equation 3. And what you see is this, again, r min over r max, r min minus 1, and this is something which is finite and good, which we can use whenever pk is not close to n, when it is not n minus 1, n, or n plus 1. But when pk is actually one of these numbers, then we get an infinite value in this gamma. And what's happening here is that when pk is one of these numbers, the AK matrix, which is the partition of the A matrix, which is available at node k, it will be close to square, right? And what happens is, in the proof of this theorem, you see at some point AK times AK transpose and the pseudo inverse. And this is actually a Graham matrix, and it will be very ill conditioned. So when you take this pseudo inverse, you will get a diverging expectation over this A matrix. As we saw in the simplified examples, right? When you divide by something that can be 0, you will have infinite expectations. The proof of this theorem is based on results on Wishart matrices and the Hart distribution. Some other important components are the unitary invariance of the Gaussian matrices and the invertibility of the square Gaussian matrix. So in the next slide, we will focus on equation 1 again. What we will do is that we take the closed form analytical expression here and plot this versus the P1 value that we saw in the previous plots. And then we will also simulate the left-hand side using simulation tools. What you see here is the blue curve is the theoretical curve, the analytical closed form expression that we found in theorem 1. And the orange crosses are the simulated empirical average of this expectation. So we simulate a bunch of times and we average what we find. And you see we have a strong support between the theory and the practice, that the curves are exactly on top of each other, which is really nice. So we really feel really good about this analytical result, that it matches the simulations. Now I'll move on to the secondary analytical result, where we look at what happens at larger iteration numbers. And the big difference between this one and what we saw in theorem 1 is that now we don't only have xk here, but we subtract the xk estimate in time t. And we still have this alpha k, which is defined in the same way as before. And we also have the same gamma here. So think of the case where you have a large generalization error in the first iteration, then it will be carried over to the left-hand side and it will just keep on being large. So what this lemma suggests is that if we have a large generalization error at some point, it will not decrease as the algorithm iterates. Yes. So we've already seen these two empirical results, where the first one is what happened in the first iteration, which we saw just now. And on the right side, you see what we saw a few slides ago, what happened after convergence, after 200 iterations. And you see that the generalization error is still really high at this point. So it's remaining high, as the lemma 2 suggests. The reason we chose not to have this as our primary result is because you see this approximation here, which was not present in the theorem 1. So we had to do some approximations to find this expression, which can be maybe further developed. And I think it lies in the future extensions of this work. So, okay, one part of what we're seeing here is the fact that the model, or one reason explaining why this is happening is the fact that the model is over-parameterized. And in general, we don't really know how to find the correct solution to the problem. And the other part is that there's some numerical instability in the pseudo-inverses that are being taken. So the obtained solution is quite far from the true solution, right? And we are under some impression that noise in the training data could help give some numerical stability to avoid these peaks. But we've seen in some derivations that it only adds up to an additive term in the generalization error, and that it will just, without assuming any noise in the solution of obtained in the algorithm, it won't really help remove this generalization error peak. But we think it requires some more research to be decisive to say what happens with the noise. Similarly, if we would have a non-zero regularization in the training, we could improve the conditioning of the matrices again to invert and give the numerical stability. However, introducing a non-zero regularization is of course done at the cost of an increased training error, but that's all fine if we get a better generalization error, right? But if you know the drill when you try to find the regularization parameter, a too large regularization will make the model not fit the training data or neither fit the test data. Or a too small regularization won't have any significant impact. But regardless of regularization, we think that our results are important to show that you shouldn't design your problem so that you lie close to these peaks at all. If you design it so you lie somewhere here in between or somewhere above here, then you're way better off to get a good solution for your problem. So before I wrap up, I want to give you some more details on the proof of the analytical results in the paper. So one large portion of finding the proof was, or deriving the proof, was to find an expression for this type of matrix, or this type of expression, where we have this Gaussian matrix C, and we have the C pseudo-inverse multiplied by C, and then we create this quadratic form with some vector set. And what we eventually found was that all that pops out of this is actually the squared 2 norm of Z multiplied by the rank of C divided by the number of columns in C. And the rank of C, since it is a Gaussian matrix, is just the minimum number of the number of rows or the number of columns. Because it's a Gaussian matrix, it will always have full rank. And it will be the lesser of these two numbers. And the proof of this little lemma here is built upon taking the singular value decomposition of the C matrix and then taking the pseudo-inverse of this singular value decomposition. And then you multiply it together and you do the trace trick and a few things like this. And then you're left with one of these unitary matrices from the singular value decomposition. And we found that this one is also a random matrix over all the unitary matrices. Following a Haar distribution. And using properties of this Haar distribution, we find this expression here. which is very key for the final result. The other part in the proof I'd like to share with you is this other lemma, which has a similar structure to the previous lemma, but a bit more complex. So here we have the pseudo-inverses inside this A-bar matrix stacked like this. So the first upper block is the first partition of the A matrix that we define in the partitioning is A1 pseudo-inverse, and then A2 pseudo-inverse stacked from the top down like this. And we have this R min and R max defined as before. And then we find this equation 8, which you see is very similar to what you saw in theorem 1. And how we find this is, again, using the lemma in the previous example, and simplifying and analyzing what happens between, for example, A1 pseudo-inverse and the matrix A2, and when you have the transpose like this, and using a lot of properties on the pseudo-inverses, a lot of algebraic tricks like that. And then eventually we find this infinite value comes from properties of the inverse Wishart distribution, which defines the distribution of A1 transpose pseudo-inverse. Yeah, so that's basically it for the key parts of the proof. So let me conclude the paper so we can take some Q&A session for this as well, and get back on track. So with this paper, we show that partitioning plays a major role for the generalization error performance in the distributed linear learning. And the general guideline that we find is that you shouldn't set any node to have the number of unknowns to estimate as the number of observations available, or close to that number either. So neither n-1, n, or n+1. We also find that if the generalization error, our results suggest that if the generalization error is large after the first iteration, it will not decrease either as the algorithm iterates. And these results, or you find this behavior when, as a result of how you design the problem. So it's not an innate property of the COCO algorithm itself, but it's more dependent on the designer of the problem, how you set it up. And future work on this topic would be to further characterize the COCO algorithm to more rigorously find more exact expressions for this lemma 2. And then further also investigate the effects of the regularization to say what happens there. How important it can be to decrease these peaks in generalization error. And then we also want to see an extension to the decentralized case and what happens there if you see the same behavior. Thank you all for listening, and please ask whatever questions you have in mind for this paper.
Great. Thank you very much, Martin, for the nice presentation. Really interesting topic, and we need works like that have very strong theoretical analysis on the generalization error. So thank you very much.
Thanks.
So going for the questions, I have also questions, but let's give the floor to the audience. Eric, you are the first. I'm allowing you to talk.
Hello, thank you for the presentation. I really enjoyed it. I was just wondering about, in the start of the presentation, you mentioned two different ways of distributing the data and how you were specifically analyzing this case where the A matrix was partitioned and divided between the users. Do you have any idea if this choice of data distribution is what leads to this ill conditioning of the matrix, or would this happen regardless of how you distribute the data?
Okay, yeah, great question. So let me just go back to the slide for a second. You saw it here, right? That we distributed by columns.
Yeah. Exactly.
I mean, the reason we distribute it by columns here is to perform this dual ascent, which is included in the COCO algorithm. So it's definitely a basis for the algorithm itself. And I mean, if you would have think if you would have similar expressions doing by rows instead, like to the left, as long as this A matrix would be near square, you would run into the same problems, I think, when the A matrix is Gaussian and it is near a square matrix, you would run into the same problem, is my intuition.
Okay.
Because that's where the problem lies, right? When you try to inverse this matrix.
Yeah, that explanation makes sense. Just a sort of follow up on that. I mean, this idea might be completely wrong, but I know that in some optimization algorithms, if you have an ill-conditioned matrix, you just add like a small constant multiplied with an identity matrix or something to make it look better. Is this something that you considered? Would this be a good idea here? Or?
I mean, that's basically the idea of regularization, right?
Yeah.
It will, since if you think of the regularized least squares cost function, you will have in your inverse, you will have this A transpose A plus lambda I. If you're familiar with that one.
Yes.
But I mean, we have simulated examples with the regularization. It is also included in the paper, some numbers on how the generalization error peak is behaving when you have regularization. And we think that while you can decrease this peak and make it rather small, we think it's still important to have this notion of like, you shouldn't design your problem like this, because you can do better if you do something else.
Okay, I understand. But when you use regularization, the peak got considerably smaller then.
Yeah. If you find the sweet spot, which you always have to do with regularization, right?
Yeah. Oh, I understand. Yeah.
But it's not. Yeah. Okay. Yeah. Thanks. Thanks for your question. Any more questions?
Yeah. So thanks, Henrik. Now Jaya has a question. Let me allow him to talk. Jaya, can you talk now?
Yes, thank you. Thanks, Martin, for this very good talk. I have one naive question. What is the difference between this generalization error and like the test error? Like this is the test error you're talking about, or?
Okay, yeah. So, yeah, it's a test error. When we say generalization error, it's really connected to the test error. So you see it here, right? The test error in itself would be given a test data point, that was not included in the training. This Y star and A star would be the test data, right? And you square it like this. You square the prediction error. But now when we talk about generalization error, we often think about like some distribution of the test data. And we take this expectation over the test data rather.
Okay. Just one more question. So here, the P values, right? It determines the number of columns that each you're distributing among different nodes.
Yeah, exactly. This PK is the number of unknowns in each node.
Number of unknowns.
So all the nodes have n observations available. They have all these A blocks has n rows, and they have PK columns like this.
Okay. So my question here is this has to do anything specific to COCOA framework? I mean, any other distributed algorithm? Like how do your results change? Like your results, I see it like it has. I mean, at least I don't see where COCOA is really playing a role. If you just say you have simple, I mean, any other distributed algorithm, right?
Yeah. Okay. So I mean, the reason we focus this one is that it is part of the framework of COCOA that distribute the data in this fashion. But you can also have like similar behavior also in like centralized solutions, which is it's a quite famous paper by I can't remember his first name, but the guy Belkin.
Yeah.
Where you have a centralized setting and you have a certain set of parameters in your two parameter vector, and you learn a subset of these parameters. And if this number of parameters in the subset is similar to the number of observations, then you run into similar behavior like this.
Yes.
So it's definitely like connected to other settings as well.
Okay. Okay. Thank you, Martin.
Thanks for the question, Jaya.
Hey, thanks, Jaya. Thanks for the nice question. So more questions, Martin? If yes, please raise your hand. Okay, no more questions, then I'll take the liberty of making my question, Martin.
Yeah, sure.
Okay, so here, as a following up on Jaya's and also Eric's question, this is more tailored towards Cocoa, right? And I think mainly because you have bounds on using random matrix theory, you have to assume that the matrix A is IID, right? Gaussian and IID. Yeah, have you thought about what happens if it's non-IID? I know that gets very nasty with random matrix, but maybe if you can use some bounds on how the matrix is non-ID, then maybe that could help. And I'm just asking this question because Cocoa is all you can say is a proto version of federated learning algorithms.
Yeah,
and
right.
Then
it's a general framework.
Yeah, and then in these algorithms, non-ID plays a very big role. So that I'm just thinking if you can move and can just translate your results to general federated learning settings. And that one way would be to having these bounds on the non-ID part and imbuing them into the random matrix part.
Yeah, so thinking back on details of the proof, like I'm trying to shoehorn in what would happen if I wouldn't have an identity covariance matrix, right? Because that would be non-IID in this Gaussian setting at least. I definitely think that the behavior would remain because if I think back on this Mikhail Belkin paper I mentioned, he also includes numerical examples on real life data, like I think the CIFAR set and also the MNIST set. So I definitely think it's a really good potential extension to this paper. To see it in the distributed setting, because what they talk about is only the centralized setting, right? So
yeah,
I think it's really important for the Cocoa framework to have such an extension.
Yeah,
and I think while it would get nasty, I think it's definitely doable, especially in the Gaussian setting.
Yeah. Things get better when you have Gaussian.
Yeah, that's always nice.
Okay, this was my question.
Yeah, thanks.
Does anyone have another question? No? Okay, then thank you very much, Martin, for the presentation. And now I welcome the other group. Let me promote you to the panel. So could you raise your hand? Ali, can see you. Oscar, yeah, raise your hand. Nice. And Said. Yeah.
Yeah, hello everyone.
Hello.
Can you see me? Okay, thank you.
Yeah, I can hear you. Do you know if your other group member is here?
Yeah, Oscar Batista, I think, is here.
Okay.
And I'm here as well.
Okay, great. So let me just introduce you.
Yeah, let me share my screen.
Yeah. Okay, just a moment.
Oh, okay.
Okay, so can you see my screen now?
Yes.
Yeah. Okay, so now let's welcome the special topic 5. And the topic is handling non-IID datasets, which is a follow-up of my question to Martin. So nice. Then the presenters we have are Ali Bemani, Oscar Bautista Gonzalez, and I think this guy is no longer in your group now for now, right?
Yeah.
Okay. So the references that this group selected are on federated learning and on the challenges of handling non-ID data on federated learning. These are very nice references, and I'm looking forward to your presentation. Please start sharing the screen whenever you like.
Thank you. Can you see my screen?
Not yet.
Okay.
Yeah, now I can.
Yeah, okay. First of all, I want to thank Ram Hussein and Marathon for this nice workshop as the organizer, and it's the last one of the topic on this workshop about the handling non-IID data set and then on the decentralized data. I'm Ali Behmani with my group member Oscar Batista Gonzalez from PhD student on the Yale University on the division of the control and automation. Okay, at the first time I will give a kind of the introduction about the federated learning, as you can see. And here nowadays we have so many devices that and a smartphone and IoT devices that have to be connected together, and it's very interesting to run some kind of machine learning algorithm over them. It's really interesting for us to run machine learning algorithm over these nodes. But the standard of the machine learning algorithm we have it's that we can run the machine learning algorithm over the server, and the server requests the data from each client and gather the data on the. Sorry, I don't know why. Okay. Maybe it's possible to run this one over the. Okay, so we wanted to run, now we have this kind of machine learning algorithm that we want to run over the server, but some kind of things that we have to consider about them is that sometimes we need to privacy this kind of data over the client, and we have a kind of the resource limit over the client for the battery capacity and battery life, and also we have kind of the latency and offline nodes during the machine learning. So we have this kind of the centralizing as a disadvantage on this method that and the way that we can do it with this kind of the collecting data, we can run the and we have the kind of the problem on the process. We can send the process on each node. Let me bring the PowerPoint. I think it's better that I choose on that one. It's better. Okay. Sorry for this interruption during this presentation. Now we wanted to use the federated learning to get the server take the one initial model and send the initial model to each of the clients, and after that ask from each client what value of the parameter, and then gather from each of the nodes in the server. And the simplest way is that we take the averaging over the parameter that from each client. This is the federated averaging that we can do for the federated learning, and we know that the federated learning is a kind of the active research during these days, and a lot of research also has been done on addressing over the challenge over the federated learning. And one of these challenges about reduce the communication cost of the transfer of huge matrices of the weight when we want to transfer from the client to the server. And it's one topic that we want to consider about them during this presentation, and also unexpected dropout of the synchronization latency. That it may be due to some kind of the network connectivity, power, and computing constraints. On the other hand, we wanted to consider about the federated learning and statistical challenge, the kind of the topics that we want to investigate over the accuracy reduction with respect to the weight divergence. Okay, so based on these things, we want to introduce the federated learning based on the two methods that we have as a federated stochastic gradient descent and federated average. Federated stochastic gradient descent. We can say that in the federated stochastic descent, each client send the gradient to the other or parameter to the server, and server can take the average from all the parameter and then send it back, turn it and send it back to each client. And because we need to frequently do this action, we need to communicate, frequently communicate between the clients and the server. But the difference between the federated stochastic gradient and federated averaging, for example, we can see here for the federated stochastic gradient descent, each client send back the model to the server, and the updating term has done during the server, and then server send back the W, the new W parameter to each client. It has a kind of the problem, and also we can see instead of sending the gradient to the server, we can send back the parameter, and the server do the action over the parameter and take the average on the parameter and send it back to each client. On the other hand, on the stochastic, on the federated averaging, we can define a kind of the mini batch over the federated stochastic gradient descent, and then if you want to apply the federated stochastic gradient descent over the mini batch, it's similar to the federated averaging algorithm. And in the federated averaging algorithm, we can, in the iterative training and update parameter, we can use gradient descent, and also clients send back the parameter and to the server, and server take the average from them and apply it to the new parameter. But in the federated averaging, we have a less communication than the federated stochastic gradient descent, and we can get a good result over this one than the federated stochastic gradient descent. And the size of the mini batch and the number of that iteration in each client, and also the fraction of the client that want to participate in this federated learning can be they can be a hyperparameter, and we can tune all of them during the iteration, during our iteration. Okay, federated averaging. Now it's a topic that we want to discuss about it, federated averaging or non-identical data. And we wanted to show that some experimental setup over that work with some kind of the data set and investigate over the accuracy reduction the Fed averaging on the non-ID data. We have used some, the algorithm have used some training over the neural network on the 3 data set, MNIST, CIFAR-10, and KWS, and KWS is the data with the 10 keywords as a keyword score. And also the training sets are partitioned into the 10 clients and distributed over 10 clients. Now we have a two kind of a scenario for this distribution data over the client. For the IID distribution, we can consider that each client randomly assign a uniform distribution from over these 10 classes, because each of these data sets has 10 classes and 10 labels. But for the non-ID distribution, we can consider that two schemes. For the first scheme of non-ID, each client receives only one partition, only one class of this data of each subset of each data set. And for the second scheme, the stored data divided into the 20 partition, and after that assigned to each client and randomly assigned. But we need to consider that each node for each client submit to the two classes of this division. So if we wanted to compare the stochastic gradient descent, federated stochastic gradient descent with the Fed average. In this comparison, all the learning rate and the decay rate are identical, but for the batch size, we can consider that the batch size in the Fed SGD 10 times larger than Fed AVG, because in the Fed AVG we run the federated learning over the client, and each client we have kind of the iteration in each client, and it's equal to the, if we consider that we have a 10 clients and each client run the iteration algorithm in each batch size, we can for the fair comparison, we can say that the batch size in the Fed SGD should be equal to 10 times larger than federated learning, federated averaging. This is the experimental result. We show that this kind of difference when we work with the non-ID data. As you can see, for example, the MNIST data set, you can see the blue line and green line only for the stochastic gradient descent and with the IID data, with the IID distribution. And the batch size is for the stochastic gradient descent, you can see here. But the difference between the federated averaging with the non-ID, you can see it's reduced for the green one and red one, and the maximum accuracy reduction for the class for the scheme 2 for the distribution data, because for the scheme 1 distribution data, because it's more exhaustive than the scheme 2. And also we can see the same for the CIFAR-10 and KWS data set, and this way although show that we have a kind of the we have working with the non-ID data, we reach with the less accuracy than working with the IID data. And the difference between the number of the iteration, number of the epoch, local epoch in each client, we haven't seen any, doesn't any large reduction, doesn't any large difference between them. For example, for the MNIST data, we see here for the epoch number 1, for the epoch equal to the 1 and the local epoch equal to the 5, we haven't seen any big difference between them for the federated average. And this is the numerical result for this running this kind of the federated averaging over this kind of data set. And as you can see, the reduction is less for the scheme 2 than the scheme 1, but for this one, for example, and N and C partner, you can see a large reduction over the accuracy than the other training for the stochastic gradient and working with the identical data, independently and identically distributed data. And it indicates that the accuracy of the set averaging may be affected by the exact data distribution that we're gonna investigate over this topic. And also here, another way, actually another way that we can use to compare the Fed averaging with the stochastic gradient descent is the weighted average divergence with the same weight initialization. And here we can define the weight divergence as the norm of the weight parameter over the Fed averaging minus the parameter in the stochastic gradient descent over the weight in the stochastic gradient. With this definition of the weight divergence, we can see the weight divergence of all layers in the neural network for all the data set increases as the data set become more non-ID. And for example, from identical from the class scheme 2 non-ID and to the scheme 1, and we know that the divergence, the weight divergence over the class 1 is more than the divergence over the class 2. So we can say that between the divergence, you can see here, we can connect it to the one kind of the parameter, mathematic valuable things as the EMD, Earth mover distance, to evaluate the weight divergence during our learning algorithm. And the EMD is a kind of the, we can consider that if we want to compare two distribution the data, we can consider that one distribution as a whole ball in the domain D and another distribution as a ball on the same domain. And we can say that EMD say that the minimum effort that we want to do to move the ball from distribution 1 to the distribution, the second distribution over this distance. So we want to use this variable to federate the averaging on the non-identical data, and the mathematical demonstration of this one. You can see here, if we consider that our data set distributed over the domain, over the subset of A, capital X, and Y distributed over the capital Y. We can consider that we have a C-class classification problem that that the domain Y equal to the classification of from 1 to C, and then we have one kind of the function for probability function that maps the X value to the S as a probability, a simplex probability, and it's equal to the Z with this condition that the summation over all classes, the summation of Zi equal to the 1 and Zi greater than equal to the 0 for all value of all the classes in our data set. So we can define the loss function as an expected value of the summation of the log loss function of Fi, and we can define this equal to the probability of each class that Y equal to the I, that this expectation. And the learning problem now becomes the minimization of this term. This is our problem. in the federated averaging, and the stochastic gradient descent, if we want to use the stochastic gradient descent to compare the weighted over the SGB and AVG, we can say that the optimization, the updating term for the weight in the SGB as a centralized, we can denote it as a C. Then we can say that the W equal to the W in the centralized equal to the W in the previous minus learning rate times the gradient of this function. And it's equal to this term, and we can say that it is the learning, the updating term for the parameter on the centralized stochastic gradient. And this is the federated mathematical demonstration of the weight divergence for the K, that when we use the K element, and we can assume that the synchronization is connected over T step, and NK is the amount of the data on the client K, and PK is the data distribution on its client, and K is the number of the client that participate in this federated averaging algorithm. And then the new term, the new model, is equal to the previous minus the updating term equal to this equation. And here we have the probability distribution or in the device K with the probability of the Y equal to the I part of the classification, the expected value of the Laplace function. Now we can define the WF MT denote the weight calculated after the M synchronization. It means that in federated averaging, after if we consider that T is the time step that the server requests the model from the all clients, and MT is the weighted calculated after the M synchronization, equal to the summation of total of the NK, the amount of the data on the client, or the total amount of data times to the WMTK. Now we can see some kind of the graph for the weight divergence over these things, and we can see here if the data is IID, then the divergence is small, and after the M synchronization also. But if our data is non-ID, in the non-ID setting, you can see that the divergence between the value becomes much larger, and the community very fast after the M synchronization. And all of these show us that these are kind of related things between the divergence, weighted divergence, and federated algorithm. So here we want to show that the proposition formulated in the bounded divergence phase, and the weight divergence after the M synchronization, you can see here, it comes from two parts. One part is related to the divergence after the M-1 synchronization divergence, and the second part is the weight divergence included by the probability distance for the distribution on client K compared with the actual distribution of the whole population, data over all clients. Based on these things, we know that our weight divergence is related to these two things, and the weight divergence synchronization for the previous one, M-1 synchronization, is amplified by this term. And the term of AK is equal to the 1 plus learning rate summation of the probability of the solution over the client K. And we know that this term always greater than the 1, and we can say this term always greater than the 1, and this divergence amplified with degraded accuracy. So the difference initial W in the we can say that also if we consider that only with this term, the different initial W in the federated learning that goes to the large weight divergence will still be encountered. And on the other hand, for the second part, if you consider that the centralized decay, then this term becomes a root cause of the weight divergence that related to the EMD that we have defined before that. And the EMD term is infected by the learning rate, which is here, and the number of the steps before synchronization, T and the gradient. So based on this equation, the error validates that EMD for the difference between the distribution, the data over each client, and the total distribution is a good metric to quantify the weight divergence for the set average. Here is some kind of experimental result for this proof that we use the training set is stored and partitioned into the 10 clients over the subset of the data, and an example per client use the 8 difference value from 0 to the 1.8 for chosen EMD as a estimate distance between these two distribution data, two kind of distribution data over the population distribution and distribution data over each client. And first, on population T over 10 classes generated for EMD, and second, a new distribution T0 is generated by shifting the 10 probability of T by 1 element. And we can see that the mean and standard deviation of the weight divergence are computed over 5 distributions for each EMD. For all the 3 data sets, the weight divergence of each layer increases with EMD, and this effect is more significant in the first convolutional layer and the last convolutional layer as the FT3, this one, and the convolution and the first convolutional layer for any data set. But if we consider if we want to show that the test accuracy with respect to the EMD and the S-moment distance, you can see after some threshold on this data set, the test accuracy started to fall, and this kind, and it means that you can see that if we only move if we only distribute a kind of the sharing data over each client and reduce the EMD before this threshold, we can improve the accuracy of the federated average. So this is the proposed solution. But as I said, that if we want to use the data sharing strategy.
Ali, sorry for interrupting you. Can you please use a headset or something? Because I can see a lot of noise from the fan.
Now, let me check my headphone, because now I think.
Now it's okay?
Now it's much better. Yeah.
Way
Okay.
better. Thank you.
Okay, sorry. So for this part of the
No, you may go to the last 20 slides maybe, and then represent all of them.
yeah,
I was
from here.
kidding. No, I was kidding. Come on.
Yeah,
Go
yeah.
on.
Thank you. So for the purpose solution of this one, and the Azure said that we can using the we can share the data, use the data sharing strategy over the all clients, and if we consider that we have a the volume of the beta is the capacity of the data share among of the little small data over the all of the data that we want to share over all clients. And we can see here with increase in the accuracy of the model, it increased by the sharing data from the 5% to 25%. And also the EMD is clear that decrease with this way with the sharing data from the server to each clients. And it's obviously it's against on the federated learning concept, because we want to preserve the security and the data on each client. But with this way, we only share, as I said, that we shared a small set only from the server to each client, and with this way we want to improve the accuracy. On the other hand, we define another parameter as an alpha, and in each synchronization or at the first time for the learning a data set, we only the part of this shared part of this data as a division of this data send it to each client. And we can see another figure with this one, the test accuracy over the alpha, that the test increase with the test accuracy over this one, and we have only work with the beta equal to the 20%, and equal with the red one, beta equal to the 10% of the global data. So it's a kind of this is the proposed solution of the Azure, and with this one, and also we can use the warm-up model with a small sharing subset. For example, I mean that in the server before that the initial parameter, we can train our model and create one warm-up model, and then send and share the subset to the other clients. Now I wanted to show some kind of the convergence analysis of this federated averaging on non-ID data from another paper. And here we need to define some analysis, the convergence of Fed averaging on non-ID, and it's only related to the mathematics. The problem formulation is equal to the minimization over W, or this function, the summation of PK. PK is the weighted of the case devices that we want of each weighted of the K devices that use in our network, and N is the number of the devices that we have used. But the reality things in here, it means that when we want to use federated averaging, we have some practical things. It means that we can consider that in each iteration, all of the clients contribute in our learning, because maybe some of the devices are off and they work as a struggler, and the server can't can't wait for all the devices response. On the other hand, the training data are non-ID, and it means that the data available locally fail to represent the overall distribution. And the algorithm description here is that the stochastic gradient descent that we want to run in each client. We can say that the gradient step for partial distribution of the client, it's look like here. And here we can define the communication cost with as this one, if we consider that T equal to the total number of every devices that contribute total number of every devices stochastic gradient descent iteration to reach to the epsilon as a convergence. And E is the number of the local iteration between two communication. We can say that the 2T over E is the number of communication that we need in our algorithm. If we want to prove for this one, we need to take some assumption over the function f1 as a smoothness, strongly convex, and variance of stochastic gradient for the function. It should be bounded with the sigma, and also the expected square norm of the stochastic gradient. It should be bounded with G2. This is the assumption that we need to prove some algorithm in this paper. And finally, we can reach to this kind of the equation inequality for the convergence over the federated averaging equal to that less than or equal to this term. And we can define this term over with the previous definition over the strongly convex and smoothness, and also bounded the variance of the stochastic gradient descent norm. We can see that some kind of the proof of theorem with this way, and but here it's the practical term, working with the practical term of these things, that because we consider that the global synchronization step is a subset and is the one subset, and it means that n is with the condition that n from 1 to n is the number of term that the server requests the parameter from the devices. And if in the practical then, if we consider that if we are in the sample t+1 is not element in this subset, it means that we haven't in the synchronization and we are in the local iteration. But if we are in this subset, then the nu w is equal to the summation of pk with a v t+1 that comes from the server. And this is some kind of the definition or the stochastic or the gradient. Then with this way, we wanted to prove that for the new updating weight, we can say that it's equal to the wt minus eta times to a stochastic gradient. With this way, if we want to go, I want to over from the proof of these things because I think we haven't enough time, but we go to the lemma 1 and lemma 2 and lemma 3 as a kind of the result for this lemma. We can use this lemma to prove the convergence equation inequality. For example, for this expectation of Vt+1 minus the optimal W, we can use that here as a gamma, and capital gamma is equal to the optimal point in overall the data minus the optimal point in each client. And it's clear that if we have a identical distribution data over the clients, the capital gamma equal to the 0. And if we have a big divergence, and the capital gamma goes to big and big. So with this way, we can say that this is the proof of this theorem that we can wanna cross over them and reach to the use of the two scheme that we want used on this convergence rate. For the index of if you consider that ST is the active devices that that contribute in this contribution of the federated learning, we can define two scheme of how to selecting these devices. If for the scheme 1, we can we can consider that the subset of the k indices randomly selected from the clients, but with the probability, the sample with a replacement probability. And with this one, we can say the aggregation step of federated averaging equal to this term. And if you consider this one, then the convergence rate, it's look like an identical distribution, but the term C added here, and we can talk about it for the next one, the effect of the other parameter on this convergence. And also another scheme is that the select k indices uniformly without replacement of the probability, and each probability we can consider equal to the 1/n. It is with this way we can say that we consider that it's because this one is a little bit different from the federated averaging, and we can consider that when we want to select in k devices from the set n, it's clear that we can scale this probability of each client and say that the aggregation step of Fed averaging equal to the n/k of the summation of this probability distribution. And then the convergence rate on this scheme is less than this parameter, and the C parameter here is equal to this one. Now we can say that with the choose of this parameter as a hyperparameter, how to reach to the different convergence. Here is we can say that the dominant term in the convergence rate equal to the order of this one, and T epsilon is the number of the required step for the Fed averaging to achieve to the epsilon accuracy. And then we know that the number of the required communication is T/E/E. And it's has a kind of the relation related with this topic. And with this term, we can say that the parameter E for this function at the first one, with increasing the E, the total is decreased, and then the total parameter is increased, the total equation. And it means that we can find the one optimal value for E. So this is one hyperparameter that we can tune during our algorithm. And also we can choose of k that the number of devices, but as you can see here, it's not really high dependency over the one, because the term that times to this one, it's 1/k, and we haven't any big influence of this one. And the choice of the sampling scheme, we defined the sampling result for the non-uniform sampling result is faster convergence than the uniform sampling result, and especially when P1 equal to the Pn are highly non-uniform, and it's clear. Okay, now I wanted to hand over the presentation to Oscar and ask him to continue for the rest of the paper. I'm going to finish my screen sharing.
Okay, can you hear me?
Yes.
Okay, perfect. I'm going to run a little bit because we are run out of time. So if you need, if you have any question, I can answer later on. So are you, can you see properly the slides?
Yeah, and the audio is also good.
Okay, perfect. So another contribution of this paper is basically, contribution of this paper is basically it shows up that there is a crucial need of learning rate decay in the federated averaging to achieve convergence in non-IID settings. And this is shown up by this theorem here, where it is shown up that with a constant learning rate and in the parameter E greater than 1, which means that there is more than one running iteration in each local node before the communication with the server, then the federated averaging converts to a suboptimal solution instead of optimal solution, even when we are using full bat size like gradient descent. And to do that, to arrive to this theorem, they use an example, a ridge regression model, which is a strongly convex and a smooth distribution optimization model. And they define basically this matrix A, which is related with the features matrix, but it is not the features matrix. And this matrix is a three-diagonal matrix and symmetric. And they create this matrix and the vector B, which are the outputs, in order to be able to divide this matrix and vector in a partial sum to be able to distribute this optimization problem among all end devices. So by using this example, the authors reached this other theorem related with the previous one, where if, as I mentioned before, if the number of running steps on each local node before the communication is greater than 1, then the convergence will reach a suboptimal solution if instead of the global optimal solution. And this can, here on these two functions, we can see the relation between the different matrix A, K, and the features matrix. So by using this matrix A, they assure that the data is a non-IID distribution of the data setting. And finally, in this paper, they create numerical experiments to demonstrate all the previous theoretical analysis. And to go through this experimental setup, they use the NIST dataset by running a logistic regression, which is strongly a smooth convex problem with 100 of clients in a non-IID fashion. And on each round, they select devices running E steps of a stochastic gradient descent and with a decaying learning rate. So it will achieve convergence according to the previous slides. And the evaluation of the average model after each global synchronization and the number of activated devices is the same among all the different examples. So, and on the top graphs on the left, we can see how this relation of the requested rounds and the local steps follows an hyperbolic function on all the data sets and the NIST balance and the synthetic ones. But it is not the case where the synthetic ones is even a more unbalanced data distribution. But it is not the case of the NIST balance where the authors require further analysis to explain the reason for that. But if the interesting thing is that, if we move to the number of clients that participates on each communication round, there is not a high effect of the number of clients that participates, even when we are talking that we have a non-IID distribution. And this is due to the fact that if B is not as much higher than C, these two parameters, then the number of clients that participates on the communication, it is not affecting as much. But on this parameter B, we can see that we have this capital parameter, which indicates the heterogeneity of the data. So it means that if the heterogeneity of the data increases, then the effect of the number of clients that participates on the communication round has a higher impact. And on the lower schemes, we have in the lower graphs, on the bottom on the left, we have the NIST balance case, and on the right part, we have the NIST unbalanced case. And as we were talking about the scheme 1 and scheme 2, scheme 1 is basically making the assumption that the server has control over the end devices that are considering to average over them. And on the scheme 2, they are making the assumption that the data is balanced. So in the lower and left case, there is no problem with these two schemes and more or less has the same convergence speed and accuracy. But on the right part, due to that scheme 2 is doing this assumption of unbalanced data, it has a higher instability and a worse convergence in compared with scheme 1. And this is solved by T-scheme 2 by making a scale local, by scaling the local objective functions instead of just making this assumption of balanced data, which is not the case on this example. So right now, going to the last paper, which is robust and communication efficient federated learning from non-IID. This paper comes up due to the fact that there is a communication overhead due to the privacy preserving collaborative learning on federated learning. So there is a need to reduce the communication cost, and the existing compression methods basically are with limited utility on this federated learning because they make some assumptions that are not realistic, such as that the compression just is done upstream from the end devices to the server, or they consider IID distribution of the data, which is not realistic, as we mentioned. So first of all, we are going to show up an evaluation of the existing methods to compress the communication. And the authors comes up with a solution, which is named sparse ternary compression based on top K gradient specification, which compress the upstream and the downstream communication. But they also apply ternarization and also an optimal Golomb encoding of the weight updates, which is a lossless encoding. And finally, we are going to see how sparse ternary compression outperforms federated averaging on the federated learning conditions. So basically, the communication cost is dominated by this expression. So the number of iterations, the communication frequency between the local nodes and the server, and the entropy of the weight updates, as well as the inefficiency of the encoding. So if we consider that a number of iterations fixed because we want to reach a certain accuracy in the size of the model, then we just can manipulate the frequency of the communication, which is done, for example, with federated averaging, the entropy of the weight updates through specification, for example, like top K specification, or even with dense quantization, which is the case of SIGN-SGD, where SIGN-SGD is basically running stochastic gradient descent, but instead of taking the full precision of the gradients, it is just taking the sign of the gradient, defining this parameter delta to take into account how much weight of this gradient is taken into account on each iteration. So taking right now, moving to the evaluation of the existing compression methods, the authors creates an experimental setup where they run two kind of training models, BG11, which is basically a non-convex problem convolutional neural network for the CIFAR10 dataset, and logistic regression, which is a convex problem for the MNIST dataset. And the training sets are partitioned into 10 clients, and we distinguish three cases. One of them is IID, dataset distribution, then non-IID with different levels of non-IID-ness of one class and other of two classes. And all the compression methods are running with momentum SGD, maintaining the same learning rate and batch sizes between the different compression methods. So on the left part, we can see how all the existing compression methods basically has the same accuracy or reach the proper accuracy in compared with the non-compression method, which is the black line, which is by default there is no compression on on the communication. But if we move on to the non-IID data settings, then we can see how all the compression methods are damaged. So if we look in the federated averaging that we were talking on the previous paper, here it's on the convex case, it is not suffering as much as just with increasing the number of iterations, it will probably reach the same accuracy that without compression. But if we look on the non-convex, it reaches even much non-stability, and this is due to the fact that it can be because the weight divergence between the clients is augmented. And on the case of sine HGD is even worse because, and this is due to the fact that when the non-IIDness degree is augmented on the clients, then the probability to reach the correct sign of the gradient that is run on each local node in compare with the true sign of the gradient, it is probably 50% more or less when it is considered a batch size of size 1. And we can see here how if we increment the batch size in IID distribution, then the probability to have the correct sign will increase. But if we have non-IID case, it will be maintained to 50%, which is basically that we are not learning at all. But we can see how the top case specification method, which is the blue line, outperforms the other ones in the non-IID settings. And this is due to the fact that there is no suffering of weight divergence because on every iteration on the end devices, after that there is a communication with the server. And in compare with sine SGD, we are not incrementing the noise of the stochastic gradient descents, the stochastic gradients through quantization. So this sparse ternary compression comes up due to this fact that top case specification outperforms the other ones in non-IID settings. But this paper also, this method, sparse ternary compression, basically adds to this top case specification a downstream compression, also with the upstream compression, a catching mechanism against partial client participation, because we are going to communicate the weight updates between the end devices and the server. So we need some kind of synchronization, and also a quantization and optimal lossless coding to reduce the entropy of the communications. So first of all, how to include this sparse sparsification, and the downstream is using this top operator, which maps the weighted updates vector without sparsification to the sparsification case. And basically we can see here on this expression how this operator is applied on each local node and finally the server average over all the contributions of the end devices. And we here define the residual in order to avoid that all the time the same elements of the weight updates are used on this communication, where basically I haven't mentioned it, but a fraction of P elements are maintained non-zero, and the rest, which are the higher ones, and the rest are set to 0. And to extend this downstream compression, upstream compression to downstream as well, this top operator is applied as well before the communication between the server and the end devices, defining this new residual, which is related with the sparsification on the server. So about the catching,
Oscar, just one point.
Yes.
Could you conclude maybe in 3 minutes so that we keep the schedule?
Yes, I know. Sorry.
Thanks.
Basically, they are just avoiding this part of partial client participation. Here I show up the algorithm that they are using to eliminate redundancy by combining sparsity with binarization. And basically the weight updates vector can have 3 values, minus, mu, 0, or mu. And this mu value is calculated by taking into account the higher values of the weight updates vector. And through this method, basically, the entropy of the communication is reduced 4 times if you compare just the sparsification method with the sparse ternary compression, which combine this sparsification and ternarization. So once we have used sparsification, quantization, then the last one is encoding. Encoding because we don't want to send the weight updates, the position of the non-zero values, the absolute position. We want to send just the distances between them. So they use this column position encoding, assuming that a random sparsity pattern taking into account that the model is big and the number of elements that are not set to zero is as well big, having a probability of success equal to the sparsity pattern. So I'm not going to go into details here. And basically where they show up experimental setup to compare this sparse ternary compression with the other existing compression methods, which are federated averaging and sign SGD, where we are just going to evaluate this case of BG, G11, and on CFAR. So to make a summary of this part, I will say that basically sparse ternary compression outperforms federated averaging and sign SGD when the non-I-ness of the data is increasing, as we can see on this part of the graphs. And as well, it happens the same where the byte sizes diminishes, even with the IID data settings. So sparse ternary compression outperforms federated averaging and sign SGD in these 3 cases when the non-I-ness of the data is increasing, there is a low participation rate, and the byte sizes is diminished. So this effect of the low participation rate can be seen as well on these graphs, where the different lines, it indicates that the dashed lines indicates that stochastic gradient descent with momentum is applied and on the other ones, just stochastic gradient descent is applied. So here we are seeing the contribution, the effect of the unbalancedness to the different methods. Basically, with 1, we are just showing up that there is data is balanced over the end devices, and with 0.9, we are just saying that is unbalanced. And we can see even with a low participation rate, the balance has no as much contribution on the effects on the accuracy of the different compression methods. And this is due to the fact maybe because with the low participation of end devices with high number of points, the rare participation of these end devices compensates the participation of devices with small subsets of data. So here, basically to conclude, we can see how sparse ternary compression outperforms the other compression methods on the communication cost, where here on the horizontal axis can we see the bits upload, and on the number of iterations as well, where it's much faster. And this experiment is done by taking into account IID data, medium batch size, let's say 100 clients, and a participation rate of 10%, which is which is favoring basically the federated averaging and sign SGD. But even with these conditions, sparse ternary compression outperforms the other existing compression methods. And finally, we can see how to reach this 84% of accuracy, sparse ternary compression has a really, really small communication cost in compare with the other ones. So to finish with this paper, just basically I want to mention that sparse ternary compression outperforms the other existing compression methods on federated learning environment or conditions. So it means that it outperforms these ones by taking into account non-IID settings, small mini batches, or a small fraction of clients participates. But on the other hand, federated averaging will be recommended if the communication is latency constrained, or if the client participation is very low and the clients hold IID data and medium big mini batches. So this paper comes up with a different approach. It comes up with going from low frequent high volume of communication, which is basically federated averaging, to a high frequent low volume approach, which is the contribution of this paper, and shows up that on federated learning, it outperforms federated averaging with this kind of compression method. And finally, just to show up again the different reference list. And sorry for being a little bit fast for this part, but we were running out of time, and we can answer the different questions that you can have. Thank you.
Okay, great. Thank you, Oscar. So we are running a bit out of time, but if someone has a question, maybe just one, I can take it. Otherwise, we have the virtual Porter sessions in the afternoon, and everyone is welcome to join the session. Okay, no question, then I suggest we stop for the lunch. For now, we have 1 hour break, and then we get back at 1. We get back here in this room just to announce the links for each virtual session. And then if you are interested in a specific topic, then just go to the virtual session. It's a different Zoom link, and we'll put the links in the chat when we get back for lunch, okay? Thank you very much for attending the session now. Thank you. See you in 1 hour.
Martin, do you want to share your screen and then put the launch there, or
yeah, I can,
or at least the program there or something like that?
Yeah, I can do that. Okay, we get back in 1 minute. Okay, so is everyone ready for the session? If you have any question or anything, just raise the hand or put a Q&A. I put now the links for the virtual sessions, and please take a look there. And for the special session 3, I suggest that you go there and could you double check if it's working properly, because I also had to create that session now. Yeah. Okay, so now we can go to each individual session if you want and start the discussion. I will be also joining one of these sessions, so please feel free to go to the session that you prefer.
Martin, I may stop YouTube streaming because we don't stay here anymore.
Yeah.
But I need to be host, I guess, to be able to do that. Or you can do that if you want.
I can give it to you because I need to go to the other session.
Henrik, you just need to ask one of your team members to stay there, and then you can go and then visit some other rooms. But at least one member should stay.
Yeah, so Jose, I'm leaving this session and going to the other one, okay?
Okay. Let me see, Martin. Believe me, I'm also confused here. So you need to go to a special topic 4, generalization error. But if you want to also join some other rooms, maybe you can stay in your room for like 20 minutes and then feel free to leave that and then go somewhere else.